think about how easily, well, relatively easily, we find our way around. Someone says, go into the kitchen and grab a soda. Simple, right?
Right. For us, usually.
But for an AI, trying to navigate a place it's never seen before, just using spoken instructions and its camera vision, that's a whole different ballgame. It's a huge challenge.
Absolutely. And today we're diving into a really interesting new approach to this problem, which is generally called vision and language navigation, or VLN.
VLN, got it.
Yeah, and let's say, standard way people have tackled VLN is, well, it's logical but maybe limited. The AI looks around,
Observes.
right, observes, tries to make sense of what it sees, and then, figures out the next step. Observe and reason.
Okay, makes sense. But I can see how that might fall apart.
Exactly.
Yeah.
Especially if the path is long or the instructions are a bit ambiguous, like trying to solve a puzzle, just looking at the piece right in front of you, ignoring the box picture.
Yeah, you'd get lost pretty quick if the goal isn't immediately obvious. But some researchers have come up with a new system, VISTA, that's VISTA, and they're proposing something that sounds much more human, actually. They call it imagine and align.
And it really is a fascinating parallel. Think about that soda example again. You're told, get a soda from the kitchen. You don't just stare blankly ahead, do you?
No, I probably picture my kitchen, maybe where the fridge is.
Precisely. You anticipate, you visualize, you use a kind of, well, imagination. It's forward-looking.
And VISTA, which, by the way, stands for Generative Visual Imagination for Vision and Language Navigation, is built around that idea. It tries to weave that proactive imagination right into the AI's process.
It combines that look-ahead ability with ways to check if those imagined scenes actually match up with reality, with what the AI is seeing right now.
And then uses structured reasoning to decide the next move.
Exactly. So our mission for this deep dive, drawing from the research paper introducing VISTA, is to really break down how it works.
And figure out why this imagine and align approach might be, a pretty big deal for AI navigation.
Let's get into it.
Okay, so let's break this down. At its core, VISTA operates on this closed loop. It's constantly cycling through 3 steps. Imagine, verify, act.
That's the fundamental cycle. First, imagine. It tries to picture a potential future state, like what the goal might look like.
Oh,
Second, verify. It compares that imagined picture against its current visual input. Does this match what I'm seeing?
Right, and then third.
Act. Based on that comparison, that alignment, it reasons about the best next action to take, move forward, turn, whatever. The paper's figure 1 gives a good visual overview of this loop.
Imagine, verify, act. It sounds simple, but the devil's in the details.
Oh, absolutely. And one of the really clever parts is how it decides what to imagine and when. It needs to balance relying on the overall instruction, like find the kitchen, versus reacting to what's right in front of it, like an unexpected chair blocking the way.
Ah, okay. Because sometimes you need the big picture, sometimes you need to deal with the immediate obstacle.
Exactly. And that's where this component called the Adaptive Imagination Scheduler, or AIS, comes in.
Adaptive Imagination Scheduler, AIS. Okay.
Its job is to dynamically switch between 2 modes of imagination. One is instruction-driven, they call it static imagination, focusing on the overall goal description.
Like picturing the kitchen.
Right. The other is observation-driven, or dynamic imagination, which is more about generating possibilities based on the current view, perhaps imagining what's around the next corner.
So how does it choose? How does the AIS decide whether to be static or dynamic?
It uses 2 key signals, or metrics.
Okay.
The first one is trajectory uncertainty.
Okay. Uncertainty, like how confused is it?
Sort of, yeah. It measures things like how many different actions seem plausible right now. Is the path it's taking deviating a lot from a straight line to where it thinks the goal is? High uncertainty means it's maybe a bit lost or unsure.
Makes sense. And the second metric?
The second is visual semantic similarity. Basically, how much does the currently observed scene look like the scene it imagined based on the instruction?
Ah, so comparing the picture in its head to the real picture.
Precisely. They use a technique called cosine similarity on image embeddings, essentially comparing the core meaning or content of the images.
Okay, so uncertainty and similarity, and there's a rule.
Yep, pretty logical one. The AIS decides to stick with the instruction-driven static imagination only if 2 conditions are met. Trajectory uncertainty is low.
Meaning it feels confident about its path.
And visual similarity is high.
Meaning what it sees matches what it expected.
Exactly. If either of those isn't true, if it's uncertain or the Rukaki doesn't match the expectation, it switches to the more reactive, observation-driven dynamic mode.
So it defaults to being goal-focused, but if things get confusing or look wrong, it becomes more adaptive to the immediate environment.
That's the idea.
Yeah.
It allows the agent to be goal-oriented, but also flexible and responsive.
Okay, that's the win. Now let's talk about the how. How does the visual imagination module actually, create these images?
Right, this is where it gets really interesting. It uses a two-stage pipeline, blending language understanding and image generation.
2 stages. Okay.
Stage 1 uses a powerful vision language model. They used Qwen2VL, which is good at describing images. It looks at a candidate scene, maybe from its training data or a previous imagination step, and generates a text description.
Like a hallway with a wooden door at the end?
Something like that, yeah. A descriptive caption. Then, Stage 2 takes that caption
The text description.
and feeds it into an image generation model. They used stable diffusion, but importantly, they fine-tuned it using a method called LoRa, specifically for this navigation context.
So it's not just any image generator, it's tweaked to make scenes relevant for finding your way around.
Exactly. It synthesizes a visual scene based on that text description generated in Stage 1.
So description to image.
And they do something else clever, too. They create what they call an in-painted image.
In-painted.
Yeah, think of it like taking the AI's current view, masking out parts of it, and then using the imagined content to fill in those masked regions.
Ah, so it blends the imagined future with the current reality, makes it more contextually relevant.
That's the goal. It helps ground the imagination in the here and now. The key takeaway is this module produces these rich, visually plausible hypotheses about what the target might look like or what might lie ahead.
Okay, so we've got this imagined picture, but the AI needs to know, does this match what's actually out there? And where should I even be looking in my current view?
Right, that's the critical verification step, and that's the job of the perceptual alignment filter, or PAF.
PAF, the reality check.
You could call it that. It acts as the bridge between imagination and perception. It takes 3 things as input: the AI's current camera view, the fully imagined scene from the module we just talked about, and that in-painted version.
Okay, current view, imagined view, blended view.
Exactly. It processes all 3 using a shared visual encoder, a ResNet 18 network in this case, to pull out the important features. Then it uses something called multi-head attention to compare and fuse these features.
Attention mechanisms.
Mhm.
Those are good at figuring out what parts relate to other parts, right?
Precisely. And the output of the PAF isn't just a yes-no. It's actually a spatial attention map.
A map, like highlighting areas on the current view.
Exactly. It's like putting a spotlight on the parts of the current camera image that are most relevant to the imagined goal. It tells the AI, hey, focus your attention here.
That's really neat. How do they train it to know where to put the spotlight?
Good question. Since they don't have perfect ground truth for where the AI should look based on an imagined future, they created pseudo-ground truth. They use another model, Grounded SAM, which can take keywords from the generated captions
Like blue sofa?
and try to find and highlight those objects in the current observation. These highlighted areas become the training target for the PAS attention map.
Ah, clever bootstrapping.
Yeah, they built a data set of about 30,000 examples, current view, imagined view, caption, pseudomask, and trained the PAF using specific loss functions to make its attention maps match those masks.
So the PAF essentially learns to translate the imagined goal into a focus point in the real world. A visual bottleneck? Kind of.
That's a great way to put it. It filters the visual input, focusing the downstream reasoning on the most relevant parts.
Okay, so imagine goal, checked against reality, focus area identified. Now the AI has to decide, what do I actually do next?
Right, and this is another place Vista differs from many older systems. Instead of just spitting out an action like move forward, it uses what they call navigational chain of thought, or COT, reasoning.
Chain of thought, like thinking step by step.
Exactly, it's structured reasoning.
Yeah.
Vista's COT process has 3 stages. First, goal grounding.
Grounding, meaning connecting the overall instruction to the immediate situation.
Yeah, like if the instruction is go to the room with the blue sofa, goal grounding might infer, okay, my current sub-goal is finding a blue sofa.
Got it. Stage 2.
Perceptual verification. This uses the current observation and that attention map from the PAF. It interprets this information to see if the current goal, the blue sofa, is actually visible and where.
So it checks if the highlighted area contains the target.
Essentially, yes. They even mention using text summaries of the attention map, like the mask highlights the object on the left.
Okay, and the third stage?
Decision justification.
Mm.
Based on the verification, it selects the next action, turn left, move forward, stop, and, crucially, it generates a reason why.
It explains itself.
They fine-tuned a language model, LMA27B, to produce this whole chain: the goal, the verification outcome, the justification, and the final action command.
And the key thing is this COTI isn't just an after-the-fact explanation, right? It's part of the actual decision loop.
That's a really important distinction. Unlike some earlier work where COTI was used for interpretability after the AI acted, here it's integrated into the control loop. The reasoning directly influences the action. Figure 2 in the paper actually shows a comparison, Vista's reasoning versus other models, highlighting how it uses that visual imagination.
Okay, this all sounds very sophisticated. Imagination, adaptive scheduling, filtering, chain of thought. But the proof is in the pudding. How did it actually perform?
Right, the results. They tested Vista thoroughly, mainly on the standard room-to-room, or R2R, dataset, which uses the Matterport 3D simulator. Very common benchmark. They also used another one called RoboThor.
R2R and RoboThor, and how did it do?
Exceptionally well, actually. On R2R, Vista set new state-of-the-art results. This is shown in Table 1 of the paper.
State-of-the-art meaning better than previous best methods.
Yes, particularly on the unseen splits of the dataset environments the AI hadn't been trained on, which is the real test. It showed significant gains in success rate, SR.
Did it find the goal?
Success weighted by path lengths, SPL.
Did it find the goal efficiently?
And navigation error, NE, how close it got. They actually had to create an auxiliary dataset just for the imagination part, R2R Imagine, with over 250,000 generated images.
Wow.
And compared to the previous best, a model called Do8 Imagine, Vista showed, I think, a 3.2% jump in SR and a 7.5% jump in SPL on the key-val unseen split. That's quite substantial in this field.
So better success, more efficient paths, especially in new places. What about RoboThor?
Similar story there. Table 3B shows the results. Vista significantly outperformed baseline models on metrics like success weighted by path length and success rate. We're talking numbers like 28.8% SWPL and 43.1% SR, big jumps over prior work in that specific setup.
And does it handle longer paths well? That seemed like a weakness of older methods.
Yes, Figure 4B suggests it does. It shows Vista maintaining higher success rates and more stable performance, even as the required path length increases. And Figure 3A gives some nice qualitative examples, showing how Vista visually connects the instruction to what it's saying.
Okay, the overall results look strong. But did they check which parts of Vista were really pulling the weight?
They did. That's where ablation studies come in. They systematically removed key components to see the impact.
Like what happens if you take out the imagination part, or the QT?
Exactly. The results are in Table 2 and Figure 4A, and they're quite telling. Removing the visual imagination module caused the biggest drop in performance, particularly in success rate and SPL.
So that forward-looking imagination is really critical.
It seems to be, yes. Taking out the chain of thought reasoning didn't tank the success rate quite as much, but it definitely hurt path efficiency, the SPL score. The paths became less direct.
Suggesting COTI helps with making smarter, more structured moves.
That's the interpretation. And removing the perceptual alignment filter, the PAF, that led to less focused visual attention and more sort of wandering or erratic trajectories.
So each piece, imagination, filtering, reasoning, really does play a distinct, important role.
It appears so. Their interplay seems key. And on RoboThor, they specifically found that visual imagination really boosted success on paths longer than 15 meters.
Makes sense. Planning ahead matters more on longer journeys.
Definitely.
Okay, so Vista looks powerful, but no system's perfect. What are the acknowledged limitations here?
The researchers are quite upfront about them. One big one is the dependence on the quality of the generated images.
Garbage in, garbage out, potentially, if the imagination is flawed.
Right. In very cluttered environments or places that look very different from the training data, the diffusion model might struggle to generate useful or accurate scenes, which could mislead the agent.
Okay, what else?
Computational cost is another. All this imagining, filtering, and reasoning takes processing power. Real-time deployment on, say, a small robot with limited compute could be a challenge right now.
Not quite ready for your average home robot yet, maybe.
Potentially not without optimization, yeah. They also mentioned that the thresholds used in the adaptive imagination scheduler deciding when to switch modes are currently set manually.
Meaning they might need tweaking for different types of environments or tasks.
Could be. And finally, the big one for a lot of robotics work, simulation versus reality.
The sim-to-real gap.
Exactly. Most testing was done in simulators. Real-world sensors have noise, lighting conditions change unexpectedly. The physics aren't quite the same. Deploying Vista on a physical robot would likely uncover new challenges.
Sure, that's always the hurdle.
But even acknowledging those limitations, Vista really does feel like a significant step. That core idea integrating proactive visual imagination Grounding it in perception and coupling it with structured reasoning is powerful.
Yeah, moving beyond just reactively observing seems key.
And the state-of-the-art results on tough benchmarks back that up, especially in those tricky, long-horizon, ambiguous scenarios. Plus, the KT adds a layer of interpretability, which is always welcome in AI.
We can sort of see why it made a decision.
A bit more clearly, yes.
Yeah.
And the implications go beyond just VLN. This idea of combining generation imagination with reasoning could be really fruitful for embodied AI in general. Think about AI agents needing to operate and plan in complex, uncertain physical spaces.
That coupling of predicting and reasoning seems very powerful.
It does.
So lots to think about here. As we wrap up, maybe something for you, the listener, to consider. What does AI imagination really mean in practice? As systems like Vista get better, how might this capability change how robots interact with our world, maybe even in our homes or workplaces?
And how do we ensure these systems are robust when they leave the simulator? Bridging that sim-to-real gap for imaginative agents is a huge ongoing challenge. Could this imagine and align strategy also be applied to completely different problems, outside of navigation entirely? Where else might prediction plus reasoning be the key?
Definitely some fascinating questions for the future.